Okay, we are live on YouTube now. All right, so as I mentioned today, the first thing I want to do is what's called persistent homology in a nutshell. And the foundational idea is actually quite simple, but when we actually dive into the details, there's a lot of algebraic structures. But the starting point, and I'm going to describe today of persistent homology at a glance, which means I'm going to give an example when my underlying data is a two-dimensional point cloud. And if you understand this example, you would understand the foundations of persistent homology. And then we can talk about how to generalize it to any other settings. So this is a setting where your data starting point is a collection of 5 points. And then they're in 2 dimensions, so they're easy to visualize here. So at the very beginning, I'm imagining I have those 5 data points on the plane. And I'm going to start growing balls surrounding those points, okay? So the homology, the concept of a homology is on the idea, if you have never seen this concept before, there is, in some sense, the dimension attached to it. So let me put it this way. If I'm talking about the concept of homology, the zero-dimensional homology is keeping track of connected component. Okay, so of course there is a definition of what's connected and what is a component. Roughly speaking, it's sort of, if I have my data, how many pieces of my data do I have? So for example, in this particular case, if my starting point is 5 points, then I have 5 components. Okay, and another example I like to use is that if you bake a bunch of cookies, you have 5 cookies, then you have 5 components, right? They're connected is because for any single point on a single cookie, you can go from one point to another. But if you have 2 cookies, if you have a point on the first cookie and a point on the second cookie, they cannot reach each other. So that means they are disconnected from each other, right? We're going to talk about the mathematical definitions later, but that is a concept. So the zero-dimensional homology is how many connected components do you have? The one-dimensional homology is essentially looking at loops. So how many loops do I have? Remember, we have the example of this is the surface of a donut, okay? If I have a surface of a donut, how many loops do you have? The answer is 2, because you have the tunnel that goes through. So I'm going to use a different color. This is the first loop, right? It's surrounding the donut hole, basically. But because it's a surface of a donut, it's kind of like hollow in the middle. So there's a secondary loop that goes along. So another way to think about the torus, the classic way of construction, is you take a piece of paper, like a rectangular paper, like this, and you glue the top to the bottom. So now you have formed a cylinder, and then you glue the end point of the cylinder. I can't really bend very well. You kind of bend the end point of the cylinder, glue together, that forms your torus. But what's happening is that in this case, there is also a loop, like here, yeah? So that's a secondary loop, then that is a second pink, okay? So now in this particular case, I'm going to have 2 loops, which is mathematically, there's 2 one-dimensional homology generators, but really there's 2 loops, and they're independent from each other, meaning that you can't morph from one to another, right, in a very vague way. The next one is what we call two-dimensional homology. And those are voids, okay? So think about a basketball and it's hollow in the middle. That is one void for you, okay? But if I punctuate my basketball, all of a sudden, like I let the air out, I no longer have that void, right? So in a sense that my basketball, when I do this, I really want to show that there's sort of some hollow space in the middle. That is a void. So this particular shape has 1 void. So dimension 2 homology has 1 generator. However, if I actually punctuate it a little bit, let's say I break a hole right here, so the air goes in and out, all of a sudden I no longer have a void, right? Because think about the concept of void, it has to be in a closed space. So now I only no longer, and in fact, this can be deformed if I kind of pull this hole really large, it really became a bowl, right? This is now became a bowl. And obviously there's no void in a bowl, okay? So on the high level, zero-dimensional homology, connected components, one-dimensional homology, loops, two-dimensional homology, voids, okay? We're going to talk about how they are formulated in the algebraic way, but today let's talk about the high level picture. Now let's get back to my data. My data is just 5 points, okay? And I would like to know what is the information coming from this data. Maybe this data is a point of sample from a circle, right? So I can just sample a bunch of points. There's 5 of those points. Maybe sample with noise, so their relative position is kind of perturbed. Okay, so let's say this is all the data I have. I have 5 points. How can I tell, what is kind of feature does it contain? The whole idea now, the second concept of persistence is instead of just looking at the homology at the current data, I'm going to look at how the homology change as kind of deform the data, or kind of, in this case, my data is 5 points. I want to see how the homology change when I have a disk surrounding every point, and then as the radius of the disk increases, okay? So if I just looking at when my parameter T is a radius parameter. So at the very beginning, it's just 5 points, and then they have 0 radius surrounding them. So at this point, I have 5 connected components, okay? So how I'm recording it is I'm going to say there is 5 different bar whose burst time is at 0, okay? So basically I have those 5 points, and I'm using color to correspond to the color of each of those components, okay? And now what I'm going to do is I'm going to increase my radius, and to see how does those sort of disks of this radius kind of interact with each other. So, for example, as I increase my radius, you think those disks grow gradually. For example, when my radius is at 1, none of those disks kind of touch each other, right? At radius 2, none of those disks touch each other. So my homology, or number of connected components, is always 5. So you can imagine for each of those components, I can track the evolution of that component. So each of those, for example, the green component, in this case, right? Well, actually, it's a little bit confusing. I'm highlighting by yellow, but let me erase this. Just to say the green component, with my pointer, it remains as its own component when my radius has increased to 2, okay? So at this point, I still have 5 components. But then what's really interesting happened is that when I arrive at radius 2.5, what's going to happen is the ball, the disk that is green is now touching the disk that is red. So it's right here, okay? So those 2 disks start kind of touching each other, and this is what I call a death event, because if I have 2 components, they merge into one of the component died, okay? So this is a death event, okay? So now, because one of the component died or disappeared, right? At this particular time, I have 5 component, all of a sudden I now have 4 components because 2 of them merge into 1 component. And then there's a death event. So I need to assign, say which component disappeared. So for this particular case, I can choose arbitrarily because all of them are born at time 0. So I can choose one of them. And in this case, let's say I'm going to choose that the green component disappeared or died. So that's exactly what's happened here. Is at 2.5, the green component died because it merged with a red component. Okay. Another way to imagine this, you can imagine this as there's 5 points, and each of the point is sort of like a cell. And as the cell grow, 2 of the cell merge into a single cell. Okay. And then you kind of to say, okay, if 2 of the cell merge into 1 of the cell continues living, but the cell that merges with the cell disappears. So in this case, it's a green cell that disappears. So in this case, the green cell is born at time 0 and died at time 2.5. So the persistence or the lifespan, so in some sense, the concept, what's called persistence, is essentially roughly equal to the concept of lifespan, which is basically how long did this component live throughout this filtration. When I say a filtration, later on we'll define it mathematically, but conceptually, the filtration is the scenario where I'm increasing the radius and looking at how the disks interact with one another. So now so the persistence of this green component, it's born at time 0, it died at time 2.5. So the lifespan is the death time minus its birth time. So 2.5 minus 0, which is 2.5. So that is a persistence of this component. Now I keep going, at radius 3, roughly, is that exactly at 3, maybe a little bit tiny past 3, is this blue component now is merging with the red component. So I go from sort of 4 component to 3 component. Okay. So, actually, wait a minute. There's some coloring changes that's not good. Yeah. So let me correct myself. So at 3, it's not the blue that is merged. It's actually the orange piece. Okay. So at radius 3, the orange piece merges with sort of the pink piece. So we decide that the pink piece is going to keep living, but the orange one is going to disappear. So the orange component disappeared at time 3. So again, the component is born at time 0. It disappeared at time 3 because it merges with the pink component. Now at time, and now I have 3 components. At time 3.2, I end up with 2 components because the blue one merged with the red component. So the blue one disappeared at time 3.2. And at 3.7, this is where everybody merged into one component, right? All those balls are touching to each other. So that is corresponding to the death of the pink component. So up until this point, I start with 5 components and I end up with 1 component. And throughout this process, I'm keeping track of how the components are born and die in terms of, and also keep track of their lifespan. This thing is called persistence barcode.
I have a question.
Yep.
For the first merge, you said we picked which one lives and which one dies arbitrarily. Are there scenarios where it is not arbitrary?
Yes. Yes. So because all those components were born at time 0, then when they merge, I can choose one of them arbitrarily. However, the typical rule is when 2 components merge, the younger component dies. The older one lives forever. Okay. So let's say I have 2 components. One is born at time 1 and one is born at time 2. And actually, let me use a picture here. Okay. If I have a component, and let's say this is time, or actually, let me use the same axis. So let's say this is time. And if I have a component, say that is born at time 1, there's a component that's born at time 2. So, and then let's say at time 4, they merge into a single component. But this is not the barcode, right? Then they become a single component. Then what we really say is the younger component, which is the one that's born late, is going to be the one who dies. Okay. So unfortunately, this is not a very appropriate joke. It's in some sense in persistent homology that the younger ones die first. Okay. All right. So now what's interesting is up until 3.7, all the component has merged into a single component. But I'm not done yet because ideally I want to go from the radius go from 0 to infinity. In practice, the radius goes from 0 to the maximal diameter of my points because afterwards nothing that interesting would happen. But for the time being, let's say I want to go to infinity radius. So then the next radius, I'm going to have radius of 4.2. Okay, so going from 3.7 to 4.2, something interesting happened. My component is still, there's one component, but I now get a loop, right? This middle part, this empty part is a loop. So because at the beginning, all the balls kind of touch each other, but then the endpoint, the radius grow big enough, they kind of close up and forming a loop. And that corresponding to this particular bar right here, because this bar is now corresponding to dimension 1 feature of homology, meaning that this corresponding to the burst time of this loop. And now I can increase the radius, and then this hole is going to shrink. And at radius 5, it's still there. At radius 5.6, it's disappeared. So now the death time of this loop is at 5.6. So now this particular bar corresponding to burst time and death time of a loop. Okay, and then if I go beyond 5.6 in this 2-dimensional thing, you know, like there's no more interesting homology potentially I could capture. Of course, there's other different definitions. Maybe there, you know, there's nothing interesting happening. So let's say I'm just going to stop there. But there's one component that is born at 0 and never dies. That is my red component. Right? The red component, you know, in this case, is the oldest component. It's keep merging with everybody else, but it never disappeared, right? So that's corresponding to this bar, okay? So now if I go back, what do I have? I have, you know, this is literally how persistent homology works. It keeps tracks of the evolution of the connected components, the loops, and, you know, in higher dimensional example, I'm going to see voids and so on. For example, if I have points sampled from the surface of a basketball, I go through this process of growing balls. At some point, all the surface disk is going to touch each other without any holes, but the middle is still kind of hollow, so we form a void. So that corresponds to the birth of a void. But in this 2D example, I don't have a void forming. I only have loop forming, okay? So you start with a point cloud data, you go through this process, and you obtain the barcode, okay? And that barcode is literally what people use for many other data analysis tasks. For example, if I can do shape comparison, I can have this point cloud sample from some geometric shape. And I go through this process, it gives me this barcode. There are several ways to represent this barcode, and we're going to see that later as well. This barcode is basically a bunch of bars, and to describe the bars, you just have a burst time and death time, okay? So the first bar is born at time 0 and is disappear at 2.5. And then the other bar, oh, actually, yeah, let me put it as an open thing, because I would like to say at 2.5 exactly, it's already merged, so it's already died. There's a different convention. Some people also use a close to include that value. And then you also have another feature, the orange feature that born at time 0 and disappear at times 3. And then you have this red component that is born at 0 and goes to infinity. And then you have this 1-dimensional feature that is born at 4.2 and disappeared at 5.6. Okay. And then of course the death time minus the burst time is a persistence. And then finally, if you look at the last line of this example, how do I do this in practice, right? Ideally, okay, I'm keeping track of how those balls interacting with each other and how the component appear, disappear, how the loops appear and disappear and so on. But how do you do this computationally? What you end up doing is what's called a simplicial complex. So at the very beginning, when my radius is of radius 0, I'm going to represent, of course, each data point to be a single point. So it's a vertex. And then as the radius grows, they're still represented as a vertex. And then when the balls or the disk touch each other, when the component merge, then there's an edge that show up in my combinatorial structure, right? So at time 2.5, the first edge show up because the two components merged. Then the second edge show up, the third edge showed up, and then the fourth edge showed up. And then at this point, all the components merge into one. And then when this edge showed up, the loop formed. right? So now your loop is represented in a combinatorial way. The loop is represented by 5 nodes, 5 vertices, and connected by 5 edges. Okay, so in the computer, it can keep track of this. So it can tell you at this point, there is a loop forming. And then when keep increasing, this particular case, I think I'm using what's called a Ribbs complex, which is basically say that for 3 disks, if they're pairwise intersection, if they pairwise intersect, I put a triangle. Okay, so now there's a triangle forming. And of course, when I'm going to 5.6, there's more triangle forming. And when the triangle comes in, that's when this loop is filled. Okay, so the third line in this picture is showing you how the persistent homology is actually computed. You know, so that's a high-level picture. Okay, you start with a point cloud data, and you compute the persistence barcode, and you compute it through the concept of simplicial complex. So what is simplicial complex? A simplicial complex of sort of 0-dimensional simplex is a vertex, a 1-dimensional simplex is an edge, a 2-dimensional simplex is a triangle, a 3-dimensional simplex is a tetrahedra. We're going to see pictures later, but this is how you compute in practice. All right. Okay, so that is the first chunk of my lecture. Is I want to give you a high-level overview of persistent homology. And it's very surprising because in some sense, this is really at the foundation, like intuitive understanding of what this object is, but it's an interesting combination between algebraic topology and computer science. Because, you know, people understand topology for a long time. People understand algebraic topology for a long time. But I would say computational topology is the one, you know, where we say, okay, let's take those topological concepts, for example, homology. Can we compute it? I mean, homology, the algorithm of computation with simplicial complex has been around for a while, but the really main idea that I would say started the whole computation topology field, one of the concept, in this case, persistent homology, is that the core idea is I don't want to look at my data at a fixed resolution. I don't want to look at it where there's a radius 0. I want to look at it as a range of parameters, right? So if you remember the picture we have from lecture 1 is, you know, when I'm drawing a picture with a bunch of dots, I need a particular radius to make sense of this data, okay? If, for example, if this case, if my point cloud even if only 5 points, if it's sampled from a circle, the time I make sense that this is coming from a circle is precisely when this circular feature is born, when those disks kind of connect with each other, okay? But the whole idea of persistent homology is looking at data across a range of parameters and essentially characterizing how does my data behave within this range of parameters and use that as a description of my data versus forcing myself to choose a particular parameter because you don't know whether that is the right parameter to choose, right? You don't know whether parameter radius 2 is the right parameter I need to use to look at this data. And another strength of persistent homology is that it's fairly robust to noise, as we will see later, is that even if this point is sampled from a circle, and if I perturb the points a little bit, I will still be able to infer using this technique that there is a circle that is coming from my data. So it's also robust to noise, okay? So there's a few properties that is really nice about persistent homology, which is a new concept on top of the classic concept of homology. But the idea is quite simple. Can I look at homology at a range of parameters? And then I can look at, you know, when does a feature appear? When does a feature disappear? Can I use this to kind of tell the difference between signal and noise? So what do I mean by that? The concept of persistence tell me the lifespan of a feature, okay? So if the bar in this case is very short, we could potentially consider them as noise in my data. And if it's a fairly long one, then it's signal, okay? So persistence has a built-in where using the concept of persistence, it quantifies what we would consider as signal versus noise. Okay, so that's a sort of another strength of persistence. Okay, any questions? Okay, so we would have a few more lectures that goes into the detail where we're going to actually do examples. We're going to compute persistent homology by hand, and it's totally doable. And then we're going to talk about how to do this for really large point cloud data and for other type of data that is not point cloud. Okay, so this is really the foundational concept, which is focused on a two-dimensional point cloud. But if you understand this, you will understand the foundation of why this tool is useful. Another thing people can do is there's a bunch of, if we talk about machine learning, there's a bunch of existing work that turns the barcode, right, which is what I call persistent barcodes, turn the barcodes into some sort of vector. And once you turn them into vector, you can actually use them for machine learning tasks. For example, I have shape 1, shape 2. Each one of them turns into a barcode, and I vectorize them. Then I can use them to do classification. If I'm thinking about graphs, I have graph 1, graph 2. I can compute also barcode for the graphs. And then I can use those barcodes. When I vectorize them, I can use them for graph classification. Okay? So there's a lot of things, but the pipeline is you start with your data, you turn into a persistence barcode, and then you can use a barcode to interface with machine learning models. Okay, all right. So my second target today is I want to give a bunch of picture examples. I kind of mentioned briefly from last lecture about existing project idea, but I want to give you a picture idea of what has been done in the past. So let me just go right into it. So this is, remember I said there's a thermal image project where on the right-hand side, those are the thermal images of people dancing in front of the camera and doing all sort of, like an awesome postures. And on the left-hand side, this is, they're using the concept of rib graph, okay? So now remember the rib graph is based on the concept of trying to look at the level of the contour of the function, or, like what part of, like imagine I have a height function here, and I'm looking at the inverse map here, and how many components are there in the inverse map of this function. So F inverse A. So if there's one component, then there's 1 point. If there's two components, there's 2 points. For example, in here, if I look at the inverse map of this function here, there are 2 components, this component and this component, that corresponding to 2 points in my thing. And I glue them together, and that become a skeleton of my posture. Okay, so you can imagine using this kind of skeleton to do shape classification. Okay, because it throws away a bunch of other things that I don't really care, but preserve essentially the components and the loops of the shape. All right, so that's the one project. The other project, which is very common, is using the mapper, which we kind of described. It's another topological descriptor to study Netflix data. So in this case, remember I said, the data I gave example for is 2-dimensional, but in this case, each data is sort of like a high dimensional data set. And then this is, again, remember mapper is roughly an approximation of rib graph as in the previous project. And then this is looking at how does sort of different, how does the movie people watch are related to each other. So for example, in this cluster, it contains 2 different users. And then the user Alice likes to watch The Godfather, Blade Runner, and then user Charles likes to watch Fight Club. And I don't know why Super Baby is there, but imagine there's noise. But the idea is try to use the mapper graph as a way to cluster the users into category where they share the same interest. Okay, so they can study using topological technique to really explore a high dimensional data set in this case. Okay. Of course, you can imagine those islands. Again, each point in here is a cluster of movie viewers. People who watch Netflix, and then islands will be corresponding to, hopefully, to users who have share a similar interest. Okay. Oh, but I do want to notice, right? I mean, because the the mapper algorithm, there's multiple different open source implementation. One of the questions from Piazza yesterday is about looking at Ayasti, which is a company that actually have a commercial-based mapper implementation. And then it looks like they also provide educational license. I have not done that because there's also a lot of open source implementation out there. But if you want to go look into educational license, let me know that we can explore that area. All right, so the next one is try to explore periodicity in time series data. And this is a really interesting field, which is basically in the field of TDA plus sort of time series analysis or signal processing. Okay, so what's really interesting about it is that if you think about time series data, right? For example, this is a sine wave. There's an inherent topology in there, because if you think about sine wave, it goes up and down, up and down, up and down. So the periodicity can be actually mapped into a loop in high dimensional space. Okay, so what did that mean? Remember persistent homology looking at loops, right? Dimension 1 homology is looking at loops. How do I get to this loop? You start with a time series thing. You take what we call delayed window embedding. We're going to have a specific lecture on this, but I want to give you a taste of it. You take a delayed window embedding. Let's say my window is of, maybe I want to make it slightly shorter. Let's say this is my window. So when I take this window, I'm going to sample a bunch of values in this window. Let's say if I sample 10 points, then every data point sample in this window, I'm going to map to a 10-dimensional point. Then I'm going to shift the window a little bit, like this. Again, I'm going to sample 10 points from my signal. So that's another 10-dimensional point. And I go along and shifting my window. At the end of the day, the entire time series signal is now mapped into a 10-dimensional point cloud data. And because this is a sine curve, what I will tell you is when I map it and I project it onto the screen, you are going to see, remember, each of the point is a 10-dimensional point. You are going to see that those delayed window embedding into 10-dimensional space is going to form a perfect circle. Okay, so there's a translation between circle or loops with respect to periodicity. So this is sort of course, the easiest example. And what the picture on the right-hand side is visualized, because when I map this to, say, a high-dimensional point cloud, I'm going to put a rainbow color surrounding it. So it depends on the angle it's formed with respect to the x-axis. I'm going to assign a color, and then I map the color back to my signal. So the color corresponding to the periodicity. So a rainbow color is 1 period, right? So this is 1 period, for example. Okay, you can do it for more complicated signal, like the later one, and you will get the same thing. And what's interesting about it, of course, not all time series only have 1 period. There's time series with different frequencies. And then when you map it to point cloud, it's going to correspond to loops of different persistence. So you're going to see some example in that. All right, so on the more applied math and pure math side, this is a paper from one of my former students in the class who did the class project. We turned out into an actual very solid research paper. The idea is what I call stratification learning. So what is the main idea? If I have a space and this is a sundial, okay, what is a sundial? You have a disk and you have a triangle attached to the disk. And when the sun is shining, you look at which hour it is of the day. But if I'm thinking about this space, there's something interesting with this space, because this is example what I said, a stratified space, meaning that if I am a little ant that is on the disk, and if I look at my little local neighborhood surrounding it, I'm on a plane, right? So I'm in a flat region. So mathematically, I'm the ant in the interior of my disk. I'm pretty much on a plane, and mathematically it's called a two-manifold. So I'm on a two-manifold piece. If I'm also in the interior of this triangle, okay, I also look at my local neighborhood. Also, I'm on a disk. So I'm also on a two-manifold. But what's weird about it is that if my end is at the intersection between my triangle and my plane, my local neighborhood, I will have to do it larger. If I'm this point, my local neighborhood looks like 3 sheets coming together. So there's the top sheet, which is the top triangle. There's a sheets to the left-hand side, and there's a sheet to the other side. So locally, I look like I'm standing on the sort of the seam of a book. So there's 3 sheets, right? There's a sheet of the triangle, there's the left part of the disk, there's the right part of the disk. So that point over there is no longer on a manifold, because the definition of a manifold is locally you are in some sort of R2, R3, R4, and so on and so forth, which is sort of Euclidean. So you locally look like a Euclidean space. But in this particular point, I just drew it right here. Locally, it's does not look like a Euclidean space. It looks like some sort of stratified space. Okay, so the whole idea of stratification learning is to say that if you give me the data, can you infer that some part of my data point belongs to one piece of the manifold and some data point belongs to the other piece of the manifold, right? So kind of separate. A direct example of stratification learning is also if I take a plane and I have data point sample from it, they are all coming from the same piece of manifold. But if I have another plane that intersect with this plane at this particular line, then if I'm standing on this line, I have 4 sheets coming together. So locally, the point on those intersections, mathematically, they are called singularities. Locally, the structure is different than any other points. So if I have point cloud sample from the space, I like to tell things apart that is in the intersection versus away from intersection. So what is the result going to be for stratification learning? If I have, say, data point sample from this space, ideally, I would tell you, okay, there is roughly 4 different clusters. There's a cluster point that is along this line of intersection. There is point, to sample from one side of the sheets. There's point on the other side of the first plane, and then the other 2 plane is also another cluster and another cluster. So one result of stratification learning using topology techniques is going to tell you there is 5 clusters that's coming from the data. Okay, and then the pink cluster, which is in the intersection, is a 0-dimensional type features, and the other 4 are the 2-dimensional type features. So one is line and one is planes. Okay, all right. So the next example, again, this is also purely from more on the applied, on the math side, where this is a project done by the math PhD students, where the idea is if I have spaces that can be decomposed. For example, in this case, the one that's shaded is one space, the one that's not shaded is another space. If I get the topological features of them, can I, for each of those space independently, can I then, when I combine those space, can I understand what is their persistence features or what is their barcode? So it's sort of like a gluing scenario. If I have 2 space, I'm trying to glue, and for each individual space, I know their topological features and what is the topological feature when I glue them together. Okay, so that is a purely sort of theoretical investigation. Then the next example is that, remember I said there's this concept of Jacobi set where a point is in the Jacobi set when the gradient of the underlying function is aligned. So there's more computational thoughts about how to compute Jacobi set. And then there is this theory called discrete Moore theory, and you want to connect the discrete Moore theory to the computation of Jacobi set. So again, this is more of an algorithm question. And we'll talk about Jacobi set later in the semester. This is an example I said that the data set I believe is actually here, is one of the students actually used Yasti's open source, but he has a commercial license, but he was investigating all the IED explosions in Afghanistan during a time period of time. So what you do is you map each of those explosion, a lot of them unfortunately suicide bombers, over the location, time, the type of bomb, and so on and so forth. And it's a high dimensional point cloud, and you can use essentially things like mapper to study this high dimensional point cloud. Okay, so one thing I do want to mention is that when you study high dimensional point clouds, usually you should combine topological techniques with more statistical techniques, and kind of to see how does topology complement existing analysis. Okay. So this is example. I just have a picture where I talk about when I say graph stability using topology data analysis. Is you try to, like one of the important part of studying robotics is how does robot's arm get hold of some object and grasp it and then be able to kind of move it around. And then so you can map, in this case, you can map the joint angle of the robot arm into a high dimensional point cloud. And then you can use topology to study it. And in this particular case, you can use persistent homology to study it, because you can imagine that maybe the configuration space of those joints would map to, say, a loop in that high dimensional space. Okay. And then, of course, this is another example of the mapper algorithm. As I mentioned before, my point cloud is a point cloud sample from, this is an example actually from the original paper, but this project is about how to speed up the computation. So let's say your point cloud is a point cloud sample from the hand, right? You have many points sample from, say, the mesh structure of the hand. And then you have a function that is a height function going from right to left. So the right points are the ones with low height, the left point are the ones with high height, or you can do curvature, okay? So now you can kind of using the mapper algorithm to obtain a shape summary of it. And then there's an entire algorithm called mapper algorithm behind it. And again, when you see this is a abstraction of my hand, right? I mean, it doesn't really look like a hand, but it does capture, there's 5 fingers. In this case, right? So you have those 5 fingers, 1, 2, 3, 4, 5, those 5 fingers. And of course, your fingertips and so on. So one of the challenge in this is that this algorithm, works really well, except it does not scale well when you have a really large point cloud. When I say large point cloud, I'm talking about 3 million, 10 million point cloud, right? So how do you do this in an efficient way? It's still a very active research area. So you can do it looking at parallel programming, distributed programming over GPU, for example. All right. The other thing is talking about uncertainty visualization. As I said, topology has been used in visualization quite a bit. And one of the interesting data that coming from especially scientific simulations are things coming from what we call ensemble visualization. So when you think about weather simulation, usually when you simulate, for example, a storm, or you simulate a wind, you are going to simulate multiple instances. And this is what's called an ensemble. Because you want to tweak your parameter in your simulation, so you kind of get a collection of the simulated event. And then what you do to make your final, say, weather prediction is you're going to take the entire ensemble of simulation and arrive at some prediction. You are never going to use one single instance of prediction. So what you can do is you can use topology to get some summary for each of those instances in your simulation. And then you can derive some sort of summary statistics across all instances. So there's a lot of usage of topology in visualizing ensemble, and specifically visualizing the uncertainty attached to the ensemble. Okay. This is the one that actually we're finalizing a book chapter hopefully soon. This is the temperature data from mice, as I mentioned from last lecture, is that you measure the core body temperature of a mouse every minute. And then the temperature is going to change at some point when they get pregnant. And then you take the topology tool, you take the time, this temperature profile, you take the delayed time embedding I was describing before, you map it to a point cloud, and then you try to look at the periodicity of that point cloud. And for example, anyone has a guess between those two, between those 4 pictures, they are the mapping of the topological profile of their temperature. Can someone tell me which profile are the ones for mice who's pregnant, and which one are the mice that is not pregnant? Any guess?
I'll guess.
Yeah.
I'll say the ones on the right are the pregnant mice.
Exactly, okay? But things become a little bit difficult because sometimes if a mice is not pregnant, but they are jet lagged, you're going to see a profile also looking like this. So it's actually hard to tell the difference between whether a mice is pregnant versus when they're jet lagged, because their body temperature also get perturbed as well. But in this particular example, the left-hand side are the not pregnant mice, the right-hand side are the pregnant mice, okay? But I can tell you that for jet-lagged mice, which is basically you shine lights at them, which is a little bit cruel to mice, right? Because they never get to sleep very well. But it's also just the story is also pretty cruel for the grad students who work with those mice because their schedule has to be flipped as well. But anyway, if you shine lights to mice and their temperature is going to be affected when they're jet lagged, and the temperature profile when you perform topological data analysis is going to be, some of them is going to be quite like as if they were pregnant. So there's more sort of machine learning you have to do to tell those populations apart. All right, so yeah, that's exactly the same. I'm going to ask you which jet-lagged mice are pregnant, right? This is even next level of cruelty. Not only you are exposing normal mice and jet-lag them, you're also jet-lagging pregnant mice and looking at what they are. So it's an interesting question. Among all those profiles, which ones are jet-lagged mice, which are also pregnant, right? So you can imagine how this problem become more and more complicated as we're using topology tool to analyzing them. But it's actually become really interesting because you also see a diversity among the profiles you see, which may be individual differences among the individual mouse. Okay. All right. So there's also sort of applications to look at using topological techniques to look at similarities among different songs, right? If I get a jazz song, if I get like, I don't know, a hip hop song, and if I can map the song or a segment, I mean, it's actually too much if you map the entire song to a high dimensional point cloud. Most likely you take a segment of it and you map to a high dimensional point cloud. And again, you can use topology to try to do classification and also study their similarities, okay? So this is actually a really interesting field. I know a few people actually work in this area actively. Is try to use, and one of the more recent ones, I will put it in a reading list. One of those line of work is actually using a sort of topological tool to try to study song, but with the perspective of detecting sort of maybe copyright violation or detecting copied songs, right? Like cover band. So if there's a song that is sung by the original singer, and then there's a cover band who sing it, and the cover band would actually introduce some of their variations of it. So you want to tell the differences between the original one and the one that is done by the cover band, for example, and what's the difference, what's the distance, what's the similarity between them. So you can do that, again, using topological tools, which is actually quite cool. But also there's also potential to use this kind of thing to detect whether certain songs has borrowed from other songs, right? If there's a similar pattern that you can detect. So pattern recognition in this kind of data. The next one is, like I said, it's a sort of sensor network coverage with local uncertainty. So this is sort of, again, you have a bunch of sensors, and if let's say each of those disks is a sensor, right? So the area that is white is the area an intruder could be standing, and none of the sensors is going to see that intruder. But this particular project focused on the ideas that maybe my sensor isn't perfect. So my sensor has a range of, if there's a disk surrounding each sensor to corresponding to the range of the sensor, that range has some sort of uncertainty band surrounding it. So you want to study, if I have some uncertainty attached to the location of the sensor, how does that change in terms of the coverage of those sensors? There's also other sort of more on the theoretical side where you can create different movement model for sensors, and you can look at how the coverage of the sensors changes over time as those sensors are moving around. So in this case, you can actually turn this into a very mathematical question, is as you change the movement pattern, or for the sensors, how does the coverage follow a certain kind of distribution? So there's a lot of interesting question here. For example, in this case, everything that is highlighted here, everything that is highlighted here are exactly where, again, the intruders can be, but the sensor is, in this case, moving around following a certain mathematical formula. There's also the idea of, remember I said there's connection between using sort of topological techniques to study the simulation of the universe. And then there is this very nice project actually partially led by researchers at University of Utah and at Norrköping in Sweden, where they were looking at how to visualize data that's coming from astronomy simulation as well as astronomy visualization, astronomy sort of observations. And then the idea is how can you use specifically, some topological tools like disperse to study data that is coming from open space. And open space also has a large collaboration with NASA as well. There's also what's called a topology guided volume exploration. This is more on the along the idea of volume rendering in graphics. So you can use topology to try to guide the segmentation of, in this case, this is a sort of the model of a tooth, right? So you want to kind of change the different volume rendering based on the topology information of it. So you can explore a lot in that. In fact, since we have someone in graphics here, I think there's still nice combination between topological techniques in graphics. This is example, of course, in the applied side where you have the birds migration, different migration trajectories. This kind of data is collected when they are putting sensors on the bird. And then when the bird is migrating between Canada and Mexico, they track their GPS locations. And then you can study this kind of trajectory data. So the idea is how do we use topological techniques to study the differences and similarities among those trajectories to try to either do prediction or just do classification. Okay. Of course, trajectory data is not constrained to bird data or bird migration data. It can be, say, for taxis, right? So there's a lot of GPS data where each taxi has a GPS, and so you know where the taxi is roughly because GPS is not accurate. So there's actually quite a bit of trajectory data in like transportation and GIS. So there's actually an active area of research who study trajectories coming from transportations. And for example, some research in that space is trying to use the GPS data from taxi to reconstruct the roadmap. Okay, so I don't know the roadmap, but I know where taxis are. So I'm going to try to estimate where the roads are from the GPS data. And then a bunch of technique in that space is using topological techniques. There's also segmentation. There is actually quite a bit of open result. This is, of course, an example of a class project, but the idea is how can I use topological techniques to for image segmentation. For example, in this case, let's say those are either tumors or cells. You try to kind of recover what the boundary is. So it's a really active research area. Try to use topology in image segmentation, especially combine topology with neural networks, because as you might know that in computer vision, like neural network is taking over 80% to 90% of the publication right now. So there is active research effort using topology in neural networks for image segmentation. Okay, all right, so I don't know how much I can cover for the remainder of my lecture, but I'm going to do as much as I can, and if we can't finish it, we'll resume next lecture at the beginning of next lecture. So there is a quote by Garner Carson. Well, I think it's coming from Garner Carson, but it has been circling around for like 20 years. So, I don't know where the origin of it, but I'm going to contribute to Garner Carson for time being, is data has shape and shape matter. And I think it's actually a really nice quote for why do we care about the topology of the shape, okay? So one of those interesting components in this is what do I mean by data having shape, okay? If I give you, remember, if I give you a bunch of points, let's say I give you a bunch of points where x-axis is sort of one variable, y-axis is another variable, right? So if the points is somehow distributed like this, right? In my plot, x-axis and y-axis, what is the shape of my data? Can anyone take a guess? What is the shape of this data? The way I drew it.
Straight line.
What's that?
A straight line, or yeah, looks like looks like a straight line.
Straight line, yeah, exactly. So that's exactly the, in some sense, in most cases, people will guess the shape of this is a straight line. But why? This is really behind linear regression, right? Okay. Then the shape of it is a line because I'm using a linear regression and I try to fit it with a line. And of course, the next example is that if my data, as I show you, look like this, what is the shape of my data?
3 disconnected components.
Yeah, 3 components or 3 clusters, right? So in some sense, the clustering is the shape of my data, right? So as you see, I can give you more and more examples, but a taste of this is that in order for me to describe the shape of data, I need to use some sort of geometry and topology. And that's precisely what's behind topological data analysis, is try to use geometric and topological information to describe the shape, okay? So as I mentioned, I will give one last example. Remember I said that if I have periodic signals, either coming from the song, coming from human voice, coming from a mathematical function, but it's some sort of periodic thing, right? And what I said before, if I do delayed window embedding, I can embed it into a point cloud, and I can use my topological techniques to detect that it's a circle in the point cloud, which then translate back to say this is a periodic data, right? So in this case, the shape is sort of, the periodicity is a word that is used to describe this shape versus maybe I can talk about it as loops or circles. Okay, that is the shape of the data. So in some other sense, you can always imagine periodic signals, the shape of it is really loops. Okay, so yeah, so this is a lot of sort of, motivational thing of why, topological data analysis care. And then I'm not going to go into detail, so I have maybe like 10 more slides, which we're going to try to cover at the beginning of the next lecture, is the basic concept of what do we consider as a graph, what is a simple graph, what is a complete graph, what is a regular graph, and what is a simplex, which is a generalization of a graph. So maybe I will cover this piece here. When I talk about simplex, the 0-dimensional simplex is a point. The 1-dimensional simplex is an edge. The 2-dimensional simplex is a triangle. And the 3-dimensional simplex is a tetrahedra. And this is not foreign for anyone who has worked with mesh. For example, this is a mesh structure of a torus. And in order to describe the surface in the computer or computatorically, you're going to represent it as essentially a 2-dimensional simplicial complex, meaning that it's going to be represented by vertices, edges, and triangles, right? So the collection of vertices, edges, and triangles describe this data. And then this happened to be because the maximum simplex in this representation is a triangle, therefore is a 2-dimensional simplicial complex. And then this is an object we work with a lot in topological data analysis. And you can imagine a graph is essentially a 1-dimensional simplicial complex because it only has vertices and edges. Because an edge, remember, is a one simplex. So a 1-dimensional simplicial complex just contains vertices and edges. So a graph, in some sense, is a special example of a simplicial complex. All right, so I'm going to end my streaming now.